Okay, in this presentation we are going to look at the gamma distribution. So what we have here is a gamma distributed random variable with parameters alpha and lambda. So that's the shape parameter alpha and the rate parameter lambda, and it's defined by the following probability density function here. Just as a sort of quick remark that there are various ways that you can configure the probability density function for the gamma distribution. This is just one particular way, but there are other variants that are mathematically equivalent to this, particularly when you use the lambda specification, the rate parameter specification. So there we have it there, the 1 over the gamma function of alpha times lambda times the exponential of minus lambda x times lambda x to the power of alpha minus 1, where x is greater than or equal to 0 and 0 otherwise. Just as a quick remark, what we have here is a definition for the gamma function, which is a mathematical identity. The gamma function of alpha is the integral from 0 to infinity of e to the minus t times t to the power of alpha minus 1 dt. Okay. Suppose that x is a gamma distributed random variable with these parameters where alpha is greater than 0 and lambda is greater than 0. What we're asked to do is calculate the expected value of the exponential of minus x. Okay, so what do we do? This is very similar to calculating the mean or deriving the mean, but just we're doing something slightly different here. So what we have to do here is get the expected value of the exponential of minus x. That is the integral from minus infinity to infinity of e to the minus x times the probability density function dx. Okay, f of x dx. Now, just as a quick remark, we can just reset the integral, the limits of the integral from 0 to infinity, because we are told explicitly that it is 0 otherwise, where x is not greater than 0. So essentially, anything outside that range of values will evaluate to 0, so we can just ignore it. Okay, that's the sort of thing you can do with definite integrals. Just reset the limits of integration if you need to, because you can just sort of say, well, it's 0 outside. Anyway, that's a digression. Okay, so here we have e to the minus x, and what I'm going to do here is bring this first component of the probability density function, which is a constant in x, 1 over the gamma function of alpha. Bring that outside the integral, treat it as a constant. So the rest of the probability density function is here. Lambda times e to the minus lambda x times lambda x to the power of alpha minus 1 dx. Okay, now just bear with me a second. What I'm going to do is actually just gather some more stuff up here and re-express what we have there. So we have e to the minus x times lambda times e to the minus lambda x. So this part here can be re-expressed as lambda to the power of alpha minus 1 times x to the power of alpha minus 1. So clearly what we're going to do is we're going to multiply lambda times lambda to the power of alpha minus 1 and just bring it outside the integral again. Okay, just clean it up a little bit more. Okay, we really could have done this in one fell swoop, but there's a lot going on here, so I just try and keep it like go in stages. So here we have it there. The expected value of e to the minus x is alpha times, lambda to the power of alpha divided by the gamma function of alpha times this definite integral here. Okay, and what we have here is an expression where both components are denominated in terms of x. Okay, so I'm going to use integration by substitution to sort of solve the rest of this. So we're going to let y equal to lambda plus 1 times x. Okay, just as a remark, that means x equals y divided by lambda plus 1. And that would actually have knock-on effects, that dx equals dy divided by lambda plus 1 also. Okay, so this is x to the power of alpha minus 1, and now it is y divided by lambda plus 1 all to the power of alpha minus 1. And dx becomes dy divided by alpha plus 1. Okay, so that is it. So essentially what we can do is just sort of start to unpack this. Okay, so just re-express this as y divided by y to the power of alpha minus 1 divided by lambda plus 1 to the power of alpha minus 1. Now you can sort of see that these two parts can be bundled up together, okay? And they can. So what we have here is just re-express the whole thing as y to the power of alpha minus 1 divided by lambda plus 1 to the power of alpha. Now essentially that is an expression that is not an expression in either x or y. Essentially it's a constant. So what happens is we can bring that out. Okay, that whole thing can just go outside our integral. Okay, so essentially I'm just going to reorganize the whole thing such that we have lambda divided by lambda plus 1 to the power of alpha times 1 over gamma of alpha, okay, times this integral here. Okay, now that's it done really. And essentially, how come things have moved so quickly? Well, what do we know about these two parts here? So this 1 over gamma of alpha times the integral of 0 to infinity of e to the minus y times y to the power of alpha minus 1 dy, that is the probability density function of the gamma distribution. Okay, so this is that's essentially how we will sort of look at this here. It's the gamma of alpha is this expression here. Okay, so when we divide both sides by the gamma function of alpha, what we're left with is 1. Okay, so this entirely evaluates to 1. So that means we are left with this expression here, lambda divided by lambda plus 1 to the power of alpha. So that is essentially our answer. Okay, so that's the exercise done.